I think it's time for us to make a multiplication table. Now, for which group, you might say, well, if I want to do S1, not the most interesting, right? And if I want to do S2, well, also not the most interesting. But things are going to get a lot more complicated when we go to S3, because we jump from 2 to 6 different elements. Okay, so let's try to fill this table out. Let's try E, 1, 2, 3, 1, 3, 2, 1, 2, 1, 3, because we know if we apply the identity first or later, we're going to get each of the individual elements. So that's an easy start. Now, what else do I know? Well, I know that if I apply 1 and 2, we know that that's its own inverse, right? Because if we switch 1 and 2 and then switch them back, we go back to where we started. So I know that's E, and similarly, I get the identity there and there. Now, I know that 1, 2, 3 times itself is not the identity because we said that had order 3. So that means the only other possibility is that, because we can only put the two E's here or here. Yes, we are using our Sudoku rules. We could think about it without, but no reason for us not to. Okay. Well, what happens if I do 1, 2, 3 times 1, 2, 3? And you could sort of see that in cycle notation, or you could actually do it. So I'm going to do 1, 2, 3, 1, 2, 3. That's the first. That's the second. Look what happened. 1 went to 3. 3 went to 2, and 2 went to 1. So I get 1, 3, 2. There and there. Okay, so that's the little table. So now this is going to be a little trickier. Remember that when we do this, right, this is going to be the first element, and this is going to be the second when we write it. So the entry here is going to be 1, 2 times 1, 2, 3, but what does that mean? Well, when I multiply, I still do the right first. So this means 1 goes to 2, which goes to 1, so 1 goes to itself. I could write it or not write it, doesn't matter. 2 goes to 3, which stays at 3, and 3 goes to 1, which goes to 2. So this is 2, 3. Okay, now what else do I have in this column? Well, I have to put 1, 3 somewhere, and I can't put it in the same column as a 1, 3, so 1, 3 has to go here, and 1, 2. So yes, we just played a little bit of Sudoku there. Let's try this one. So let's say I want to know 1, 2, 3 times 1, 2, which means the 1, 2 happens first. Well, 1 goes to 2, which goes to 3. 3 just goes back to 1, and 2 goes to 1, which goes back to 2, so I just get 1, 3 here. So I have 1, 3 there. Now, I have to put a 2, 3 in one of these two slots. I can't put it here because there's already a 2, 3 in that column. So I get 1, 2 there. Getting a little bit closer. Getting a little closer. Let's try 1, 3, 2, 1, 2. Okay? So 1 goes to 2, which goes to 1. So 1 goes to itself. I could write it or not. 2 goes to 1, which goes to 3, and 3 goes back to 2 because, well, this doesn't move it at all. So I get 2, 3 there. And I know I have to put a 1, 3 somewhere in this. Actually, I didn't need to do that at all. With a 1, 3 here and here, the only place for the 1, 3 to go is there, and this means that has to be 1, 2. As a matter of fact, without doing any multiplication, with a 1, 2 here and here, I have to put a 1, 2 there. I have to put my 1, 3 there and my 2, 3 there. It's the only way so I don't get the same element twice in one row. So I'm really getting down to the bottom here. What do I have? I have a 1, 2, 3 and a 1, 2 that needs to go here and here and here and here. So let's do one of these. Let's do 1, 2 times 1, 3. Well, 1 goes to 3, which stays there. 3 goes to 1, which goes to 2, and 2 goes back to 1. So this is 1, 3, 2. That means this one is 1, 2, 3. This has to be 1, 3, 2 because it must appear in this column. In this row, we get this. That implies we have that. And I get 1, 2, 3. Notice that this is not an abelian group, which we already knew, but you can see that this is not the same as that. You can't reflect it over this axis. This little thing here, if I were to ignore all of this and all of that, that would be an abelian group. It's a subgroup that sits inside F3. So you might want to consider what that might be isomorphic to. But we're actually done with the table right now. Now, I want to bring up a table that you might have seen if you watched the dihedral group video. So let me just pause this and find it. This one. So no, too small. Well, we could fix that. Okay. So what I want to do is cover up my face. If I can't see you, you can't see me, right? There we go. Okay. So I want you to look at these two tables carefully. Is there a way to just change the names in order to turn one of these into the other? So if you're looking carefully, notice that the F corresponds to 1, 2, but not only that, every place in the table where you see an F, over here, you see a 1, 2. Every single one. Look at where the F's are, and look at where the 1, 2's are. And the same is true for the 1, 3 and the RF and the 2, 3 and the R squared F, and the R and the 1, 2, 3 and the R squared and the 1, 3, 2. These are the same group. S3 is actually isomorphic. To D3. So we have found a new group of order 6, S3, but it wasn't entirely new because we already knew it under different names. Only the names had been changed. Now you might say, wait a second, did we just go through all of this work and pain in learning all of these new notations to just find that the symmetric groups are always the dihedral groups? And the answer is no. Obviously no, if you think about the fact that S2 is not isomorphic to D2. S2 only has 2 elements in it, and D2 has 4 elements in it. And of course, S, like 100, has a lot more elements than D100. D100 has only 200 elements, but S100 has 100 factorial, which is a truly insane number. But in the 6th case, we only know of one group which happens to be non-abelian and have, meaning doesn't commute, and have 6 elements so far. Is there another? Or is there only one? It's a good question, something to think about and ponder.